detection. Any other? Separation. Column is not detecting anything. Only separation.
So if we have all data preserved like you.
Carrier flow. So every time your peak timings written collected from natural resources. So you may get very component will you will get hydrogen combination peak of oxygen. In this application, oxygen, nitrogen, CO2, CO, CH4, all the components will be injected in a mixture scatter into GC. The GC will give the representation of all the individual components with a peak like this. They will get separated into all the component levels. How they get separated? We will use one column, GC column. Have you seen the column last few days? How many types of column you have seen? One type of column we have seen, I think. Capillary column. This ID is very small. That can be from 0.25 mm to 0.53 mm. Normally we use three types of capillary column. It depends on their ID. 0.25 mm, very narrow bore capillary column, and the next one is 0.32 mm ID. This is medium bore capillary column, and 0.53 is called mega bore capillary column, similar to packed column. So now we will hear packed column. Earlier we have learned about capillary column, which is basically open tube and coated with chemicals. It's made of fused silica, fragile. You have seen touched? No. So today we will even touch and feel that columns means it is very fragile, capillary. And now you will learn about packed column. The name says packed, filled with chemical. The capillary was coated with chemical, internally coated. Basically it's an open tube, internally coated with chemical. And packed column is filled with chemical, made of stainless steel. Sometimes in earlier days you might have heard about glass column. That also packed column. That also filled with chemical. It is made of glass. And ID almost 1/4 inch. Nowadays this glass column reduced in use. You will see stainless steel made of stainless steel packed column. ID is 1/8 inch.
So this capillary column material is used glass or metal?
Capillary column is fused silica.
Material is
Inside material.
no outside.
Outside material is fused silica, made of fused silica. And packed column made of stainless steel. ID 1/8 inch. Sometimes you may see 1/16 inch also. So 1/8 inch and 1/16 inch. 1/16 is very rare used, and 1/8 is mostly used. This is capillary column internally coated with chemical, basically open tube. This is packed column. It's filled with chemical. This ID is 0.25 to 0.53 mm. And this ID is 1/8 inch, 1/16 inch, and sometimes 1/4 inch. Made of stainless steel, packed column, made of glass, and sometimes made of Teflon also. Mostly used stainless steel. So what is the major difference between these columns? Is the ID, very small ID, and it's a higher side ID 1 by 8, 1 by 16, 1 by 4. So if you inject any sample into capillary column, you will see it look like this. Typically capillary column peak, sharp peak. Base is very less. And in packed column, you can see the base is very large. Normally peak will look like this. It's a typical packed column peaks. Capillary column peaks you will see very sharp. And even in 0 to 5 minutes, you can get 10 to 12 peaks. And if you use packed column, 0 to 5 minutes, 1 or 2, 3 peaks you can see. In 30 minutes you can get 6, 7, 8 peaks. In capillary column, if you use 30 minutes, you can get even 50 peaks also. Because peaks are very sharp and take very less time to elevate. So, which column will be better? Obviously capillary column, because it will take very less time to elute all the components. Your productivity will be increased. So why to use packed column? You should not use it. It will take too much time. And peaks are very broad type peaks. But all the columns have their own specialty. In GC, we use many types of detectors. How many detectors you have heard in last 5 to 10?
VDA, water, diode.
This is not GC detector. GC detector. GC detector. How many detectors you have heard? Basically, you have trained on GCMS. Normally, MS is also a detector. So, other than MS, you have heard FID. Okay? And any other? So there are so many detectors can be used in GC, like FID, flame ionization detector, TCD, thermal conductivity detector, NPD, nitrogen phosphorus detector, or ECD, electron capture detector, FPD, flame photometric detector. So many detectors are there. In FID, you have already learned. FID means flame ionization detector. In this detector, you can get only hydrocarbon peak. So your sample contains any hydrocarbon will be detected in FID. So in this mixture, if you inject this mixture into any column, that mixture will be separated, right? But after the column, one detector is there, it should detect. Otherwise, you will not get the peak. Column's purpose is separation and detector purpose is detection. After separation, it should detect all the components one by one in different time, so that you can get all the components representation. Peak is the components representation. So if your detector FID detects only hydrocarbon, so if you inject this mixture, you will get only one peak, right? This is the hydrocarbon, and that can be detected in FID only. So is this detector a complete detector? No. It's a specific detector. It detects only hydrocarbons. If your sample contains only hydrocarbon, you will get peak in FID. So what is the use of this? Use of this, like it has very high sensitivity. It can detect even 0.5 ppmc 1 meter. So it's a very high sensitivity. Very low concentrated hydrocarbons you can detect in FID. So now you will learn about TCD, thermal conductivity detector. It's a universal detector. It can detect anything, but sensitivity is poor. TCD, thermal conductivity detector. It can detect anything. while FID detects only hydrocarbon. So which detector is good compared to FID? TCD is okay for us because it can detect anything, right? But its sensitivity is poor. When if you inject 0.5 ppm methane, it will be detected in FID, you will get quick. But if you inject even 10 ppm methane, so you will not get any quick in TCD. For percentage level, TCD is okay. It can then I can tell that TCD is universal detector.
So,
Yeah.
so which component is responsible for
Detector.
this?
It can, as I told, it can detect anything. So before going to explain the detector details, we need to know how it works. There is a Wheaton bridge that two filaments are inside the detector and two filaments are in its electronic parts. So inside TCD there is two filaments. It is kept in a box, heated box. That filament are inside in a tube. On one side we have installed one column, maybe pack column or capillary column, and one side only tube. You know carrier gas. Without carrier gas, your sample cannot be moved to detector. That carrier gas will carry your analytes through the column and they get separated within the column and elute one by one to the detectors and then atmosphere. So here, suppose we are using carrier gas argon. TCD has dual entrance. In FID we have seen a single entrance, means your column end will go to FID. You have seen already FID? Right? No? Okay. I will explain also FID. So in FID, in TCD, you are giving carrier gas argon. Your argon is going through the column and go to the TCD, and your carrier gas will emit from here. Same argon carrier gas also is going, but there is no column. It is directly going to this filament and emits outside. We are giving same carrier flow to both the lines. So at the outlet you will get same flow of argon, right? If you measure, there is maybe 20 ml per minute. Here also 20 ml per minute. Now I am giving voltage to these two filaments. Same voltage I am applying. So this is filament. So you will get some resistance value. If you input some power like 5 volts, 6 volts, if you are giving, you will get some resistance here. Like here, if you are giving inputs to this two filaments like 6 volt, as a result you are getting here maybe 25 ohms resistance. Here also you will get same resistance. Why? Because these filaments are same in size, same in length, and also same carrier is going through these filaments. So argon has some thermal conductivity. So the thermal conductivity also impact this resistance. If you change to any other gas, carrier gas, like you move from argon to helium, so this resistance value will be changed due to different thermal conductivity. Helium's thermal conductivity is different than argon. So if your carrier gas thermal conductivity is changed, that this value also will be changed. Now I am injecting any samples, maybe I am injecting hydrogen here because this is analytical channel. So hydrogen will going through this column. That hydrogen will be carried by argon carrier gas. So when I am not injecting any gases, only argon is there. So difference value is 0. So the 0 difference value, you can make that graphic in your computer. You can see the representation of 0 value, 0 difference value is a straight baseline because that value is not changing. Na? We are not injecting anything. Only argon is going through the column. Suddenly I am injecting any other gases, maybe hydrogen or helium, 1 ml, something very less amount. I have injected in this line. So your argon will carry that hydrogen through this filament for certain period, for some seconds. That hydrogen thermal conductivity is different than argon. So this value will be impacted. Maybe it will change to 50 ohm. Depends on difference between your carrier gas and analytes. So that value changes will directly impact your baseline. That your baseline will be increased. And in TC, your argon is always flowing, na? So your argon will carry your hydrogen for some seconds. It will disturb the resistance because different thermal conductivity, and it will go away to atmosphere. Then your baseline drop down. And the column purpose is separation. If you inject a mixture with hydrogen and CO2, now what happens? Your hydrogen will come first. You will get a first tip of hydrogen. After that, CO2 will move to this filament. Again, CO2 will disturb that filament because again CO2 thermal conductivity is different than argon. Again, this value will be changed. Maybe this time change to 30 ohm. Again, difference of 5 ohm. So it will again increase. This time the increment is very less because the changes is very less compared to earlier components. So you will get a smaller peak than hydrogen. This is CO2. So this is area, right? This is a shape, maybe triangle or whatever, any shape. You can get its area. You don't need to calculate, software will calculate. Okay. So you will get some area. That area is directly proportional to concentration. If you inject higher concentration of hydrogen, you will get a bigger peak, you will get bigger area. If you inject very less amount of CO2, you will get a very small peak, the area will be very less.
But there will be a saturation point will come. Suppose you cannot increase more than that limit of that maximum
all
limit.
the
Although
saturation limits also there.
Limit is there.
So we have set the instrument up to 100% and it should not saturate. That will be within frame. Nowadays all the G systems are equipped with 100% saturation that can sustain. The amplifier capacity is increased.
So
we have.
I'm talking about in the terms of concentrations. Like if you go on increasing the concentrations,
You cannot go beyond 100%.
right.
So we have calibrated the system up to 100%, that it should not saturate. In earlier days, it used to saturate. Now, all the amplifiers are built like this, that the sensitivity is divided into 2-3 parts. If we want to inject the 90%, 80%, even 100% concentration, that time we have reduced the sensitivity. So that it should not saturate, it should be within frame. So you need to know about your components concentration. Know in the sense you should have some idea of it, but detection related things is different for everybody. There I have described how TCD works. So to work with TCD, your carrier gas and your analyze thermal conductivity you need to know. That means the thermal conductivity difference is higher, then sensitivity also higher. If you are using argon as a carrier gas and or if you are using nitrogen as a carrier gas and you need to analyze CO2. Nitrogen and CO2 thermal conductivity, there is no such difference. So that time you will not get a very good peak for CO2. So recommended carrier gas for analyzing CO2, argon is okay, or helium or hydrogen. In DC we can use 4 type of carrier gas. Hydrogen sometimes used as a carrier gas. It's a little bit risky, so sometimes used hydrogen. And other 3 gases are widely used: helium, nitrogen, argon. These 3 gases are widely used for as carrier gas in GC, gas chromatography. And also sometimes hydrogen also used as carrier gas, a very special case. In these 4 gases, helium is very costly, but if you use helium, definitely you will get a very good peak, because helium's thermal conductivity is very less than any other analyze. So you will get very good response. Still, it is not very responsive detector, because it works on the principle of thermal conductivity. In FID, it's a different way. But in TCD, we are working on the difference of thermal conductivity, and it does not have such difference, very less difference. So you will get a small peak. That's why if you are using TCD, your sample should have in percentage level, even 0.5%, that is okay, but not in very less ppm level. 10 ppm, 20 ppm, it cannot detect. So when our sample is not hydrocarbon, not that cannot be detected in FID, then we will use TCD. At the starting, I have said you that why to use TCD, because its sensitivity is very less. When FID can detect even 0.5 ppm, but in TCD it is in percentage level 0.5%. It can start from 0.2%. But when we have some components like they are non-hydrocarbons, we want to detect hydrogen. What to do? It cannot be detected in FID. So you have to use TCD. No way. That time what happens? You have to inject your sample in a a larger volume, so that you will get a detectable peak. We can say that this is a peak. Okay. So you have to inject a large volume in TCD. In ml. Normally TCD used for gas analysis. Most of the cases, 95% cases, we will use TCD for gas analysis.
Volatile gas.
Yeah. Like hydrogen, oxygen, nitrogen, methane also gases that can be detected in FID. But if you are injecting a mixture, when some hydrocarbons also and non-hydrocarbons also there. So which detector to be used? TCD, so that all the components can be detected. If you are using only FID, so only hydrocarbon will do that detection will not be complete. Your analysis will not be complete. So you got your answer, ma'am?
Yes.
Sometimes we use combination of 2 detectors, TCD and FID. When we have sample like some hydrogen, oxygen, nitrogen, methane, CO, etc. CO and CO2 response is very less in TCD. Even if you are injecting 1% CO2 or CO, you will get very less small peak in TCD. So if you have a sample contains CO and CO2 in ppm level and other gases are in percentage level, so what to do? Which detector you want to use? You have TCD and FID. Some non-hydrocarbons are there, some hydrocarbons also there, and CO2 are very less amount. We want to detect all the components. So we have to use both the detector. TCD is non-destructive in nature. If you are injecting any sample in a column, and at the column outlet you are installing TCD detector. So TCD is non-destructive in nature. That means your analyte will not be destroyed when it will go through the detector. So at the TCD detector outlet, all the samples will be unchanged. So TCD detector outlet can be taken and it can be given to FID detector. So some component will be detected in TCD and some hydrocarbons will be detected in FID. So we will get some peaks in TCD and some peaks in FID. And sometimes you can get double peaks of same component in both the detector. If your sample contains methane and it's a percentage level, that will give peak in TCD and same time that will give peak in FID also. Because methane is hydrocarbon, it can be detected in FID very well, and it is in percentage level, and so at the same time it can be detected in TCD also.
Sir,
Yes.
at the same time, TCD and FID, both detector used.
Yeah, can be used. There is a way how to use. I will show you. Because TCD is non-destructive in nature, so TCD outlet can be given to FID with a simple tube. There is no need to additional column. Like this, your injector and then your column and then TCD this is analytical channel and this is reference channel. TCD is reference is required to balance the bridge, and TCD outlet is taken into FID. So if you inject any sample here, that sample will be going to the TCD and you will get some peak. And the same time the outlet is given to FID. So in a FID channel you get two channels in your computer display. And the same component, if it is hydrocarbon, you will also get a peak in FID line. This is FID and this is TCD. In both the channel you will get peak, and this FID peak will be slightly delayed. Because after TCD it will go to FID. Upon fraction of second it will be delayed. You understand this?
So in same instrument is possible?
Yes, it is possible.
It is possible.
I will show you. The instrument installed there, na? And this concept is used. It is called Analyser GC, customized GC, turnkey analyzer. When a complex mixture cannot be analyzed in a single column and a single detector, then the GC will be configured like this way. This is called special analyzer.
So if there is any sample don't know about the compound, if it is hydrocarbon or other things, so you preferably you follow these two TCD and FID in the fast process, fast in the
First of all, don't inject any unknown content say things into this.
but
Yeah. I don't misguide you. I don't need to misguide you. You are right.
If it is known, sir, there is no need to do.
There's no need to inject in this, right? Yeah, definitely you can do, but be cautious. Like all the column, you cannot inject anything into a single column. There are separate columns available for different type of analysis. Like there are so many packed column also there, like capillary column. You have heard so many capillary column, PG5, PG1, like this. There are so many packed column available in the market for different applications. like Corapac Q. You've heard this name? Corapac column. Molecular shift, carboxane. So many names are there. If you are using molecular shift column, MS, short name. In molecular shift column, you cannot inject CO2 because molecular shift column traps CO2. Your sample contains CO2 will be trapped in this column. Other components will elute. So your analysis will not be completed, and you will get some. You should have some confusion why one page is not coming. And if you do this repetitively, then your column will be saturated with CO2, and time to throw away the column. Your column will be damaged. That's why I told you, any unknown sample, anything, simply don't inject into GC. You should have correct some idea what are the possible components. If you still don't know anything, I need to inject, then you have to take some risk. If your column damage, use another. Before that, you just consult with any application person. It's a 5 minutes phone call. So column purpose is, can you tell? Can you anyone? What is the purpose of the column?
Detect the correct compound.
Detection. Okay. Any other? Separation. Column is not detecting anything.
Separation of the.
Only separation.
So if we have all data preserved like UV, IR, NMR, then we use GC.
Yes, GC have
Because
very
we have
so many applications in GC. So many still now. GC is a very useful tool.
So if it is NMR is done, the NMR for the single compound. What is the need of GC?
GC's need is separation, a complex mixture of gases or a complex mixture of liquids. Okay, it's a basic tool for separation. In GC, you can get two things: component name and its concentration. Yes. So in GC you will get two things: component name and its concentration. But GC will give these two things in indirect way. Not directly, it can give you the concentration and their name. If you inject a known standard, you have one standard, you have some methanol and ethanol, mixture of methanol and the concentration also because you have prepared the concentration, like 30% methanol and 70% ethanol, a mixture I have prepared and injected into GC. So definitely you will get two peaks. If you are using hydrocarbon detector like FID, you will get two peaks, methanol and ethanol. Two peaks like this. We are getting methanol and ethanol. And the concentration because you have prepared that mixture. Concentration MeOH is 30% and ethanol is 70%. So as a result, you are getting two peaks. So this is basic purpose is separation. So directly it will separate, and it is representing with the two peaks. And in the software you will get two area. Like this area is calculated like this. This is 200 millivolt area you are getting, and here for ETOH you are getting 300 millivolt. So write down the area, because you are injecting 30% of methanol. So if you inject again that same mixture, again you will get 200 millivolt area for MeOH and 300 millivolt area for ETOH. So it is repeatable. So any scientific instrument result should be repeatable if you are injecting same components, right? So note down the area, like for 200, reverse it, back calculation. For 200 millivolt you are injecting 30% MUH. Now you inject a mixture, unknown mixture of these two components, but concentration is unknown. Definitely you will get two peaks because mixture there are two hydrocarbons mixture and you are injecting, so you will get two peaks. This time you will get a small peak and this is a large peak. Again you will get area. That area you can see in software. This time area here area is 100 millivolt is coming. So can you tell the concentration? I already told you that area is directly proportional to concentration. Now tell me how much methanol is it? Because if you inject 30% methanol, you will get 200 millivolt area. So here I am getting 100 millivolt area. So what is the concentration?
15.
So it's a direct way or indirect way to get the concentration? Indirect way. You need one standard. First you need to inject the standard and note down the area. Now you tally with your sample. So GC cannot give you concentration directly. You should have some standard. You need to do calibration. That is called calibration. You don't need to calculate outside in your notebook. The software will calculate. But one time you have to tell that this area means that much of concentration. Then all next onwards all the sample can be tallied automatically. So one time you have to calibrate the system with your standard. If you are using GC, you should have standard. Without standard, you will not get concentration. You can get an area. You can have some idea how many components are there. You can count the peak. You are giving a mixture to GC. You are getting 5 peaks. So you can get some idea that I have 5 components in this mixture. But if you don't have standard, you cannot tell the concentration. Now the name of the concentration, identification. How it identifies? How to get the concentration? You learned clear, na? Nice. So the area is directly proportional to concentration. Now name. So every time your peak timings, retention time will not change. It will come at the same time every day. If you are injecting very less amount, your peak will be very less, but it will not change its time. Means 0, 2, 3, 4. At 2 minutes every day you will get methanol peak. If you don't change its carrier gas or temperature, instrumental parameter you should not change, then you will get every day same times. Means same peak at same time. Your timings will not be changed. That is called retention time. Okay. So if you tell the software that at 2 minutes methanol will come, next time unknown component you have injected into GC, at 2 minutes you are getting a peak, so it will automatically identify the methanol is here. Again, you should have calibration standard. One time you have to tell that at 2 minutes methanol is there, at 5 minutes ethanol is there, at 8 minutes propanol is there. So retention time wise naming and area wise concentration fitting. One time you have to do. That is called calibration. So inside calibration there are two processes. What are the processes? Retention time wise naming and area wise concentration fitting. These two processes. Simply. You can do these things. All are software friendly, young generation. Yeah? सॉफ्टवेयर हम लोग को क्या होगा? वी आर इंडियन. जिंदगी में पैसे देके सॉफ्टवेयर नहीं खरीदा ना. एनी क्रैक जहाँ इधर से फ्री में मिले सब लोग यूज करते हैं. इंस्ट्रूमेंट का बेसिक समझ गया और सॉफ्टवेयर का यूज. दैट इज इजी. मीथेन, नाइट्रोजन, CO2, any other? SO2. SO2, even H2S also there. They've got some sulfur smell, right? Methane. Sometimes, because it is collected from natural resources, so you may get very less amount of oxygen also. Okay. Why to analyze the biogas? To check the purity, right? So we need to know about impurities. Our main concern is methane. It's a main product. And also we will get some impurities. That's why we are using, that's why we are analyzing these gases into the GC to check the purity. My product is okay or not. So some other gases also there. Even sometimes CO. These are percentage level. Nitrogen also. Oxygen 0 to 1%. 0 to 1%. It is also 0 to 1%. Same 0 to 3-4%, 2%. ppm level. Even 1% can be seen. ppm level. 1, 2, 3, 4, 5, 6, 7 gases. Sometimes ethane also seen, can be seen. If we want to analyze extended level of biogas, many other gases can be added. Some higher hydrocarbons, ethylene, sometimes acetylene also there. They are very interested about, neglected. Mainly these gases are analyzed usually for biogas analysis. So, if you are using TCD, which gas can be detected? Hydrogen. All the gases can be detected because universal. But if you are checking their concentration, this is also ppm. This is okay for TCD in percentage level. This is okay for TCD. 1% is okay for TCD. O2 0 to 1% okay for TCD. ppm level not okay for TCD. Not okay for TCD. H2S very low sensitivity in TCD. If I consider ppm level, that can be detected. But if you consider in percentage level, that then okay for TCD. So challenge is here. This one, this one, this one. So our GC configuration will be like this. Our injector, then column that will be separated to this column, then TCD, then FID. So in our computer there will be two channels, one TCD, second one FID, and if you inject this mixture, what happens? Your first component will be hydrogen. When you inject in a column any mixture, so what will be the elution order? If you are injecting hydrogen, oxygen, CO2, three components in a column. So column is a separation tool. All the components will go through this column and they will get separated. All the components will elute at different times. That will reach into the detector in different times. So if you inject three components, hydrogen, oxygen, CO2, You have any idea which component will come first? Which component will disturb the detector first? Which component? CO2. Three components, just forget this. Hydrogen, oxygen and CO2. Three components are there. If you are injecting this mixture of three components into any column, at the outlet all the components will not come at the same time. They will elute at different times. That's why you are getting different peaks at different times. Column is the separation tool. When all the components going through the column, they will get separated. They will separated and they will be eluted at different times. So hydrogen, oxygen, nitrogen, among three components, which component will come first? Which component will elute first? Hydrogen. Okay. Then oxygen. Okay. Then CO2. In which basics you are telling this? Mass. Mass by charge ratio is a MS properties and it is detection related things, not elution, separation related things. M by Z is a detection related things in mass detector. But it's a we have to tell the columns properties. Which things restricted them to come out? Which things restricted them for separation? Which things is responsible for separation? Which thing is responsible for different times elution? Why not at the same time they are injecting? The same time they are eluting. Why not at the same time they are eluting? Which things restricted them? Why hydrogen first? Why CO2 come at the last? Why? So there are three things involved. Number one, molecular weight. The elution order depends on molecular weight. Among three components, hydrogen molecular weight is less compared to other two components. So the lower molecular weight will come first, higher molecular weight come later on, last. So hydrogen peak will come first, and then O2, and then CO2. Everything molecular weight. Number two, if you injecting any liquid component into the mixture of GC, you can take boiling point. The low boiling point component will come first and high boiling point component will come last. So if you are injecting a mixture of water and methanol, so here methanol boiling point is around 69 degrees and water 100 degrees centigrade. So definitely first peak will be of methanol and the second peak will be of water. So second thing is boiling point applicable for liquid sample. Now there are different columns available. I am mixing CO and CH4 also. So now 5 components. Can anyone tell me the elution order?
First CH4, then CO.
So I am adding these two components with these 3 components. So now 5 components. Now tell me the elution order. Using this theory, all other gases, so forget about boiling point. Using this theory, can you tell me the elution order?
First hydrogen, then oxygen, CH4, CO and CO2.
Based on the molecular weight. Sometimes it fails. This theory fails. We are using two different columns. One column named Orapac Q. In capillary column you have heard Tg1 ms, Tg5 ms. You have heard, right? For regarding your MS training, different column names you have heard. No? There are thousands of columns available in the market. Which chemicals are there inside the column. Depends on separation, we will decide which column to be used. So here for packed column, I am telling you two columns names. One column is named pora pack and other column is molecular sieve, MS. Here main contents is porous polymer. And here main contents is zeolites. How many peaks you should get? 5 peaks, right? Here what happens? You will get hydrogen, combination peak of oxygen, nitrogen, then CO, then CH4. So this is hydrogen. This is combined peak of oxygen plus nitrogen. And this is CO, this is CH4. This column, porous polymer, cannot separate oxygen and nitrogen. You will get a combined peak. Your oxygen and nitrogen will not get separated. Okay, I am adding O2 and 2 also. So 6 components are there. So I am adding here CO2. So hydrogen, oxygen, nitrogen cannot be separated. CO first, then CH4, then CO2 for pora pack column. Same 6 mixture of same components. If you are injecting into molecular sieve column, this time you will get hydrogen, oxygen, nitrogen, CH4, CO. This column can clearly separate oxygen and nitrogen, and CH4 first, then CO. And for this column, CO first, then CH4. So number 3 is affinity to the content inside the column. The column material depends on column material. Affinity in the sense that so many things can be like their absorption, polarity. So many things can be. It's collectively called affinity.
Sir, one more question. TCD and FID both are
They are detector.
Then CH4, why not pick is
Okay. All the components are in percentage level, right? Think about percentage level.
Previously you told us CH4 is a hydrocarbon and FID is detect first.
This is the biogas concentration. Now I am telling about column details. So I am using all the in percentage level. Means you can rely on the TCD detector. It can detect everything. So how column works? Now I am explaining column related things. So which column to be used also?
Same person doing different column and sample is same.
Yeah.
So how to?
Yes. You need to know about columns.
Yeah.
That's why I am explaining these two types of columns, because we will all go to molecular weight related basic things. Na? For elution related, you are getting 6 peaks, so you will definitely go that hydrogen will come first, CO2 come, then as madam said CH4, then CO2 as per molecular weight. But sometimes affinity will be there. Then same component, only I have changed the column. Now CH4 part, then CO.
So how to publish then?
Yeah, it is very difficult to tell which components. That means it is very difficult to identify which components. Then you have to inject one by one single component to note down. And you are not the first person to using this column. There's already established methods are there available. You know, you just buy the column, you get the literature. You know everything. What can be done with this column? What will be the elution order? That all are available. So you are not the first person to doing this. Yes, you are doing research purpose. You are making your own column. Then you have to inject one by one and note down the retention time. That definitely you can do. You will do. Coming days will be scientist. You will do. So it is very difficult to identify the peak name. If it is only molecular weight or only boiling point, it is okay, no problem. But
So this demonstration, can it is possible in this instrument in today or
yes,
tomorrow?
yes. Tomorrow I will not be. Today only. Actually, I am not application person. I am field engineer. I am actually configuring this type of analyzer DC. I built this type of DC. In this application, biogas analyzer, to detect all the components, only one column is not sufficient. Because if you are using Purapack, this separation will not be done. Oxygen nitrogen cannot be separated. Also, CO and CH4 separation is very poor. So my purpose will not be solved. If you are using this column only, molecular C, then all the components will be separated, but CO2 will not come out. CO2 will be here. Yeah, I told you earlier that molecular C column will trap CO2. It should not be injected into this column. If you do this repeatedly, then it will be saturated with CO2, then you need to throw away this column. And column is cost almost 8,000 to 1.5 lakhs. So what to do? We have to analyze all the components. We need separate peaks for all the components. In a single column, it is not possible. We will use both the columns in a very tactical way, so that CO2 should not go into this column. Again, we will get a clear peak of CO2 also. That will be demonstrated in lab.